Chapter 4.2, Place Value or Positional Value Numeration Systems. So in this chapter, we're going to be looking a little bit closer to home. We'll start off talking about the basic definition of a place value system, then we'll see that this is the system that we're most used to, followed by a few other systems that are going to be very related to our numeration system. So in a place value or positional value system, the value of the symbol depends on its position in the representation of the number. So this is the most common type of numeration system in the world today, and the specific most common place value system in use is the Hindu-Arabic numeration system, which we use in English. So a true positional value system requires a base and a set of symbols, including a symbol for 0 and one for each counting number less than the base. The most common place value system is the base 10 system, also known as the decimal number system. So our system is a base 10 system because we have our ones position, our tens position, our hundreds, our thousands, our 10,000, each are a power of 10, the base. And we have a symbol for 0 and a symbol up through 10. But when we look at why is this called a positional system? Why does the place, the position, what does that mean? Well, if we look back at the additive systems, for example, or the ciphered systems, the position that we placed our symbols in doesn't really matter. So by convention, we like to list things in order, but when each symbol represents, this is the thousands symbol, and I have 5 of them, so I have 5,000, it doesn't matter if I then put the tens on the left or the right of that, because I can just add everything together, right? But in the positional value systems, I need to know exactly where numbers are placed. 1, 2, 3, it has 100, 2 tens, and 3 ones, whereas 3, 2, 1 has 3 hundreds, 2 tens, and 1 1. So it matters what order I write the numbers in. So let's explore the Hindu-Arabic system a little bit more in depth. So of course we know we have these numbers 0 and then 1 through 9. We don't have a symbol for 10 because 10 is the base itself and is made up of the symbols 1 and 0. So in the Hindu-Arabic system, the positional values are then the powers of 10, starting 1, which is 10 to the 0 power, 10, 10 squared, 10 cubed, 10 to the 4th, 10 to the 5th. In other words, the tens, the hundreds, thousands, 10,000s, and so on. Now, to write a number in what is called expanded form, we expand the numeral by multiplying the first digit on the right by 1, the second digit from the right by 10, third digit by 10 squared, which is 100, and so on. So in general, we multiply the digit n places from the right by 10 to the n minus 1 to show a number in that expanded form. We're going to need this, which is going to feel like you know how to do this. We're going to need this to apply to other number systems where it's not going to be it's not going to be something that you've been doing since kindergarten. So, 1, 2, 3, 4 in expanded form has the 1 in the thousands place, the 2 in the hundreds place, the 3 in the tens place, and the 4 in the ones place. So we can write this out expanded as 1 times 1,000 plus 2 times 100 plus 3 times 10 plus 4 times 1. This tells me 4 in the ones, 3 in the tens, 200s, 1,000, all added together gets us this number. Now if we want to apply this to other numeration systems, we're going to have to figure out how to work with other bases, but it's going to work in a very similar way. The only thing that's really going to change is instead of the powers of 10, we'll have other positional values. So to start, we'll look at the Babylonian numerals. So Babylonian numerals are the oldest known, about 2500 BC, numeration system that resembles a place value system. So it resembles a place value system with a base of 60, which is called a sexagesimal system. But the reason it is not a true place value system is because it lacks a symbol for 0, which leads to a lot of confusion and ambiguity. Because if you think about it, if we in our system didn't have a symbol for 0, then writing the number 103 would just be 1, 3, which we could then read as 13, right? So this can cause a lot of confusion. Essentially what they would do is they would just add a big gap when there was a 0. But how do we measure multiple zeros? How do we know the gap is enough to say how many zeros there are? Also, if we wanted to end our number with a 0, 100, for example, 100, we just write the number 1. How would we know how many zeros follow it? It was a major problem in this system, and it's why it hasn't survived till today. But an interesting thing about this system is the question of, well, why 60? 60 is such a high number. Why would we choose a base of 60? So we can answer the question of why we chose a base of 10 like this, right? This is why we use a base 10 system. It's because 10 fingers, it allows for counting easily. So the base 60 system actually comes from a similar place. They would count on their hands as well, but how do you get to 60 on your hands? Only 10 fingers, right? What they would do is they would essentially count knuckles on their fingers. So 1, 2, 3, counting with their thumb, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then once you get to one round of 12, you put finger up on your other hand. Go to 12 again, another finger up, that's 24, 36, 48, and then 5 of them is 60. So once you do 5 rounds of counting out the 12 knuckles on your 4 fingers, you get 60. And so that's kind of where this base system came from. A lot of systems, their numbers come from something that we can do, like counting, that we can do on, something very convenient that everybody has. So now let's explore how we can convert to and from this system. So first we take note of what the positional values are. So like I said, they're powers of 60. We always start with 1. Every system has the ones place. Then in this case we have the 60s, the 60 squareds, which is 3600, the 60 cubes, which is 216,000, and 60 to the 4th, 5th, 6th, etc. So a gap is left between characters to distinguish place values. Again, a larger gap is left if there is a 0, but there has to be a gap anyway just to say, like, this is the first number, this is the second number, because if you notice, the Babylonian numerals, there's only really 2 parts to them. There's a 1s and a 10s. You'll see what I mean by that once we see a picture of a number in action. But reading from right to left, we then say the first group is the 1s place, so we multiply it by 1. The second group is the 60s place, so it's times 60. The third group is the 60 squareds place, multiplied by 60 squared, and so on. So if I wanted to write the following Babylonian numeral in Hindu Arabic, what I would do first is I would notice where are the gaps. So in this case, there is one gap here, right there. So this tells me there are 2 positions, and we're going to assume there are no zeros here, that there isn't enough gap to have accounted for a 0. So we'll have the first 2 positions being the 1s and the 60s, like so. So I place each of my numerals on over a position. I like to write it out, right? So I have my 1s place, my 60s place, and I write a little line, and I put that in that position so I can separate them nicely. Now we want to first start by translating the number into its Hindu Arabic, translating each symbol into its Hindu Arabic version. So in the 1s place we have 2 of these arrows which represent 10 and 1 of the 1s. And in the 60s we have 3 of the 10s and 4 of the 1s. So altogether what they mean, 3 10s, 4 1s is 34, 2 10s, 1 1 is 21. We have 34 in the 60s place and 21 in the 1s place. But this does not mean the number is 3,421. Because this is not in base 10. We need to utilize these positional values. So we take, in any positional value system, we're going to take the number in the position and multiply by the position itself. Multiply by the position itself, and then add everything together. So 34 times 60 plus 21 times 1. Together, that's 2040 plus 21, which is 2061. And so that is what this represents in Babylonian, 2061. So going in one direction isn't too bad if you can remember that that process. First translate, then multiply, add, multiply, add, right? That's it. If there are more positions, we do the same thing. We just multiply, add, multiply, add. But when we are going in the opposite direction, when we start from a Hindu Arabic numeral and we want to write it as a Babylonian numeral, that's always the trickier way to go. So we have this process. And this will be the same process we use in the next system we look at, as well as in when we look at different bases in the next chapter. So we start by dividing the given number by the largest power of 60, or the largest positional value, less than or equal to that number. Then we just repeat this using whatever remainder we get until we reach the ones place. And then we check our work by basically doing this process. And then we translate once we're done. So 7,223, we want the largest power that is less. So the largest power that is less, 216,000 is too much. But 3,600 is less than 7,223. So we are going to divide 7,223 by 3,600. Now when we do this, we get 2 with a remainder. But what does that mean? I write this as 2R23. Okay, but this means, R means remainder. If you don't remember what a remainder is, let's explore an easier number for you to picture. So let's take, for example, 13 divided by 4. Okay, so 13 divided by 4 is 3 1/4, right? That's the mixed number version of it. Now, how do I know that? I know this because 3 times 4 is 12, and then 1 more is 13, right? But how can I get that using numbers that I can't just do kind of quickly in my head because they're low numbers? Essentially, where we get this from is we have 3 times 4 equals 12, and then 13 minus 12 equals 1. And so the remainder is 1. So we write this as 3R1 if we wanted to write it in sort of remainder format. So how can I do that with the 7,223? Well, if I take 7,223 and divide it by 3,600, I get specifically it's like 2.00638, blah, blah, blah. I don't care. It doesn't matter what all of this is. I don't care about this. Point is I get 2 and then some remainder. Now, there are more than one way to find the remainder, but the way I'm going to teach is basically doing this process. We subtract the quotient times the divisor. So in this case, the quotient was 3, the divisor is 4. I take that, 3 times 4, 12. I subtract it from the dividend, which was 13. So here, that means I take 7,223 minus 3,600 times 2. 3,600 times 2, which is 7,200. And that's going to equal 23. So that's where that remainder comes from. So we're going to have to know this process. We're going to repeat this process multiple times in these problems. So make sure you practice figuring out how to get your remainder. It's always the same process. It's always this number times this number, subtract this from this number. That's how we get the remainder. Okay, so now what do I do with 2R23? Well, the 2 gets placed in the 3,600th place up here. The 23 gets taken down into step 2 because we repeat step 1 using the remainder. So I will take 23, figure out what is the power of 60 that is less than or equal to that number. So So in this case, technically 60 is not less, and we'll see why I'm just going to write this out, that if I did 23 divided by 60, if I put this, again, you want to do this in a calculator, 23 divided by 60, it's technically 0.333 repeating. So it's 0 with a remainder. The remainder is going to be the entire number because it was too high, because this number is greater than 23. But we can get that by going, well, what is 23 minus 0 times 60? Which is, in other words, 0 times 60 is 0, so 23 minus 0, we get our remainder of 23. Okay, so I place a 0 in the 60's place, and then I move on to the next one. 23 divided by 1 equals 23 with a remainder of 0, because 23 can be divided by 1. Anything can be divided by 1, and it just gives us something without a remainder. So that tells me that 23 is going to be my ones position, and that is it. So once we start here, we just kind of take each position, we make sure to fill them in. We can skip over positions where the number is too high. We just have to remember to place a 0 where it is. So don't just skip the position entirely, place that 0. Only the Babylonians like to skip their zeros. Now, how do we check our work? Because there's a lot of room for error in problems like this, especially if you don't fully understand how to get the remainder properly. So we can check our work by taking this and finding the Hindu-Arabic version. So remember, multiply, add, right? So I'll go 2 times 3600 plus 0 times 60 plus 23 times 1, and as long as that actually equals 7,223, which it does, that means we got it right. And so we can finish by actually translating into the Babylonian system. So here we have 2 ones, and then for 2 of the ones for our 3600s, and then for the ones position, we get 2 10s and 3 of the ones, like so. And again, there is no 0 in Babylonian, so we just leave it blank. So it's just like a big gap between them. And that's it. Now let's take a look at a little bit trickier type of system that's still positional value, but the position values are not as uniform. So the Mayan numerals are, the differences we have for Mayan numerals are, you can see there's like a lot more numbers to remember or to study, but they are also written vertically, starting from the units place on the bottom, units being the ones place on the bottom, the ones place on the bottom, then the next row is the 20s place. The next row is the 18 times 20s place. Then it's the 18 times 20 squared, the 18 times 20 cubed, the 18 times 20 the fourth, and so on. So we start establishing a pattern around here, but this doesn't really reflect exactly the pattern, like where did the 18 come in, but then the only thing that's changing after we put in the 18 is we're now taking the 20 to different powers. It's very strange. So remembering how to do that conversion is going to be the most difficult part of doing this, because otherwise it is the same process as everything else. The only other different is that we write it vertically, but that's not like that's not changing anything otherwise. So if we wanted to write this number below in Hindu-Arabic, we would start by noting the positions. So this is our ones position, our 20s position, our 18 times 20, our 18 times 20 squared, right? Those are our positions. And then we do the same thing where we multiply and then add, multiply, add, right? We do the same exact thing. So we need to translate, of course. The first one, it translates into 2. So it'll be 2 times 18 times 20 squared. 18 times 20 squared being 7,200, which is 14,400. The next one is going to be 8 times the 18 times 20, so 8 times 360, which equals 2,880. Next, it's going to be 0 times the 20s position, so 0 20s is 0. And then finally, it'll be 4 times 1 is 4. And to finish it out, we add all of these pieces up to get 17,284 in Hindu Arabic. So, again, as long as you remember what the positional values are, it's going to be that repeated process, right? But remembering the positions for this one is more difficult because they don't fit as nice a pattern as they do as just 60 to a power, right? So going in the opposite direction is going to be the same process as before, but again, we have to take note of these weird positional values. So if we wanted to write 4,025 as a Mayan numeral, we do the same thing we did to get the Babylonian numeral. We divide the given number by the largest positional value less than or equal to that number. So we need to know our positional values. We repeat that using the remainder until we get down to the ones place, and then we check and translate. So in this case, the largest positional value less than 4,025 is 18 times 20, which is 360. I'll just go back for a second to show, since I don't have their what this actually represents, but 18 times 20 squared is 7,200, right? 7,200 is more than 4,025, so we don't want that one. We're going to pick 360. So we'll have a 360s place, and then a 20s place, and then a 1s place. So we start by taking 4,025 and divide by 360. When we do this, 4,025 divided by 360 equals specifically 11.1805, and going on, right? So when we do this, we don't care about this part. We just take the 11, and we have to find the remainder in the same way we did before. We find the remainder by subtracting 11 times 360 from 4,025. So 11 times 360 is 3960. So we're subtracting 3960 from 4025. And we get 65 out of it. So 4,025 minus 3960 equals 65. And now we move on and we go to the next step. After we place our 11 in its designated 360s position. So now I take 65 and I repeat 65 divided by 20. 65 divided by 20 is 3 with a remainder of 5. This one we might be able to figure out on our own where this comes from without the calculator. That 3 times 20 is 60, and there's 5 left over. So 3 remainder 5. So we place the 3 in the 20s position, and we take the 5 down to the 1s. 5 divided by 1 is, of course, just 5, so that will be my last place value. And now we check to make sure that we got all of that right by doing the multiply and add. Multiply, add. Multiply, add. Multiply. Right? So 11 times 360 plus 3 times 20 plus 5 times 1 does in fact equal 4025. So that tells us we did it right, and we just need to finish up by actually translating. So to do the translation, we go find the 11, the 3, and the 5, and we write them out in order.